Okay, so if you don't know already, I play chess and I have to say, I'm pretty good at it. I said I'm pretty good at it. There you go. That being said, this channel isn't about chess, at least not until I run out of content. However, there is a lot going on in the chess programming community recently with famous programmers like Code Bullet. Never mind, that was 5 years ago. Well, Sebastian Lake, never mind, that was 3 years ago. Wow, have these years really gone by that fast? Well, anyways, I decided why not give it a try, as it can't be that hard, right? So this video is about me making a chess bot, but since I'm actually gonna go into the details about how I make it and actually make it properly, I'm only gonna cover the move making and the board representation. This is also so I can drag this out into a 10 video series and exploit my viewers for views. And also, I'm making this as my first C++ project because I thought that was a good idea. What could go wrong, right? Anyways, with that out of the way, let's get right into it. So firstly, let's lay out our plan. To make a chess bot, we have to use an algorithm that's called Minimax, which I discussed in this checkers video, which you should totally go check out, by the way. This might seem quite nerdy or daunting, but I can actually assure you that the algorithm's pretty simple. The main aim of any chess engine is to get the best possible move in the position. For example, this is a pretty good move since it wins material, but sadly, it's also gonna probably give Levy a stroke since he just takes back with the pawn, and congratulations, you lose the queen. But rewind for a second. Maybe instead of looking for what we can do, we can also look at what our opponent's responses to our move is, which that he takes our queen. Then the bot would realize how stupid the move is and not make it. But wait another second. Let's look at our response to our opponent's response if he's going to take it. It leaves us open for a checkmate, which is actually much better than losing the queen, and this is essentially the entire algorithm. In order to find our move, we look at all our opponent's moves and find the best one to counter our move. And to find this move, we need to look at our best move to counter their move. But obviously, we can't do this forever, so at some depth, we can just look at the final position and evaluate it based on the material on both sides. Then we can choose a position with the best score and return it. For this algorithm, we need essentially 3 parts. Number 1 is a way to find all the possible moves, number 2 is a way to make a move, and number 3 is a way to evaluate a position. Currently, we're missing out on all 3, which is kind of like what they call me. No brains, no bronze, no bit. But I will not go into depth about the evaluation, so let's just focus on the first 2. You probably already have in mind how we can do this. If we represent each piece with a number, we can store all the pieces in a 2D array and we're done. Okay, that's it for this video. Like and subscribe and make sure to put on notifications and... Just kidding, this is ridiculously inefficient. If we want our chess engine to be remotely fast, we need to represent our board in a more compact way so we can easily copy and interpret information from each board to the next. So what's the solution? Numbers. A really big ass number. See this number? It's a pretty good estimate of America's national debt, but it also represents something else. If you show it in binary, it still doesn't look that special, but if you rearrange the lines, it still doesn't look that special. But if you look really closely, you might recognize that this is the starting pieces of a chessboard. Of course, you can't distinguish what piece this is, but you can distinguish the location of all the pieces on the board. To fix this, you can give each piece their own unique number, and voila, you have a unique representation of the board. This is called a bitboard, because you're representing a board with bits. Damn it, who makes these names? Obviously, you probably got a few complaints, and for starters, 2 pieces can be on the same square, which is obviously not good, but a larger complaint is why would we go through all this effort just to make an abomination that is a pain to read, which is kinda true. Like, I'm pretty sure I need glasses from reading all the 1s and 0s on my screen. Just kidding, I'm a programmer, of course I already have glasses. But using a number actually has a lot of benefits. Number 1, computers generally like numbers, which allow most operations to become quite efficient and fast, which is what I need. And number 2, Bitwise Operations. Apparently, some genius at IBM decided that after all his binary manipulation, he was like, I need to share my suffering with others, and didn't take out these bit manipulation functions. But that's actually good because they are very useful. For example, if I want to get a bitboard containing all the positions of the white sliding pieces, I can just OR them all together. Best part, this is crazy fast. Like, it might be even faster than 1 + 1, and that's not even an exaggeration. So to make a move given a from square and a to square, we can create a bitboard with a bit at the from square and to square like this. Then we can OR the to square to the pieces bitboard and XOR the from square from the pieces bitboard. And bam, we can already make most moves. For moves like en passant and castling, we can actually just hard code it as they are just edge cases. But a lot of you may still be like, okay, cool, so you can represent a board with a number, but how does this help us generate a move? Well, look at this bitboard. You might be like, that's a weird position, when will I ever encounter that? And you'd be right, but this isn't a position. It's actually all the movement squares for a rook. And if we generate this for all the possible squares, we can get all the squares that a rook can move to while it's on that square. This lets us pre-compute all the rook's moves rather than finding out on the spot, which is much faster. Easy, right? Well, we're actually missing out one crucial detail, which is enemy and friendly pieces can block the rook from moving to those squares. Well, shit, I guess it's time to give up, which is what I would say if I was a player. Instead, we can actually still pre-compute it by memorizing every single possibility. Anyways, you might realize that there can be billions and billions of chess positions, and it's frankly impossible to memorize all of them. But you'd actually be wrong, since we only care about the pieces that are blocking our path. Firstly, let's just get all the possible blockers, which would be all the black and white pieces. This means that if we AND all the pieces on the board with our movement mask, this allows us to shorten the number of positions that we have to consider per square from this number to only this number. Let's try again to understand what we want to do. So given any position, we want to find which squares our rook can move to, which would be represented using a bitboard like this. To do this, we look at all the pieces that are in our rook's movement mask. Now that we have this position, we can just pre-compute all the squares that our rook can move to in the form of a bitboard, and use this as a key to find the squares. We also assume that the rook can move onto a blocker, which I'll explain why later. But wait, if you look again, you might realize that we actually don't need to consider the last square on each end, because with or without these squares, our rook would always be able to move to the end, further shortening the total number of possibilities to 4096. You also might be asking, how do I know it's 4096? Well, actually, you can count the number of positions we need to consider by looking at this position where the rook can access the most squares, which is 12, and use this number as an exponent to get 2 to the power of 12, which is 4096. Okay, got that? No? Yeah, me neither, so let's revise it one more time. Our aim is to get all the moves a rook can make based on position. To do this, we can pre-compute it by getting all the moves a rook can make beforehand for every position that it would encounter. A chessboard has a lot of positions though, but thankfully we only need to consider the pieces that are obstructing its path. If we assume that all the pieces are enemy pieces, we can allow the rook to move to them, which would make the very last square in each direction irrelevant, because the rook can always move there. If we do this for each square, then voila, we have all the positions for every square of the rook. Then we can just find out manually which squares our rook can move to for every one of these positions. Now if we do this entire process for the bishop too, we not only can find it out for the bishop, but we can also find it out for the queen, since it is just a combination of the rook and the bishop. Okay, great, now we just have to store it. Now, as I've said, we will be using this as a key to store the movement squares. Your first idea is to probably use a hash map, but actually hash maps are quite inefficient, which would destroy all the work that we've put in to get to this speed. Thankfully, there's another method, as we can store it in a giant array. Remember how I said that this position can be used as a key? Well, it can actually also be used as an index. Well, that's not totally right, but it's also not totally wrong either. Using the position itself as an index to a fixed size array would be way too big. Like, remember this number? Yeah, according to my calculations, that will be at least 2 exabytes of data, which isn't that much for data storage standards, but it is 144 million times my RAM, so that's not happening. But instead, we can use the first few digits of it in binary as our index. However, with how the numbers are being represented, there will definitely be 2 positions that have the same index. Thankfully though, there's another way to solve this, as instead of using the position straight up as the index, we can multiply it by some random number and use the first digits of the product as our index. Now you might notice that it's still possible for a collision to happen, but that's why this number is not random. It's magic. No, but it's actually called a magic number. Since we know our data set from the start, we can actually just try out many magic numbers and just find one that gives us an index that's unique. Then we can store this magic number and use it basically forever. Now obviously, finding one magic number that works for all the bishop and rook positions is basically impossible, but what we can do is find a random number that works for all the 4096 positions for a single square. Then just find 64 of these random numbers that can be used for each square. And we're done! We have successfully found a way to pre-compute every single possible position that a rook or bishop can make on a certain square. So now, if we want to look up all the possible moves of a rook on this square, we can find its movement mask, AND it with the pieces, times it by its magic number, and use this index to find a bitboard which represents all the squares that it can move to. But wait, the rook can still move on to friendly pieces. So we finally just NAND this with the white piece bitboard to get the final movement bitboard. For knights, pawns, and kings, we don't really need to do this since they move in really simple ways. So we just use some simple logic and we can actually pre-compute their attack scores since it's always fixed. Okay, cool. So now we have a functional chess game which obeys the rules of chess.
NANI? No. Wait.
Okay, never mind, we have to do checks and pins. So for checks, it's actually remarkably easy. To see whether the king is in check, instead of seeing whether the enemy pieces are checking the king, we can see whether the king can check the enemy pieces. What? Yeah, look at this. We can assume that the king is a queen and get the movement square bitboard that we discussed earlier. Now if the rook, bishop, or queen is on one of these paths, that would mean that it is in check. Well, not exactly, since rooks won't be able to check if it's on the diagonal, but all that means we have to do is an additional check of whether it's pairable. And for knights it's even easier. We can just use the attack score of the knight from the king's perspective to look for any knights that can check us. Using this strategy, we can also see whether the king is in double check, which is when two pieces are checking the king at once. Now after we realize that we're in check, we can store a bitboard that contains the line which the piece is checking us from, which is important to know how we can resolve the check. To get this line, we can use a bitboard manipulation again by ANDing the king's movement squares with the movement mask of the enemy's location, and this mask which is a rook's mask or bishop mask, depending on the direction, which I'll just call the directional mask. Okay, now how do we respond? Well, it's actually quite simple. So for any check, there are only three responses. You can either take the piece, block with another piece, or move the king to an area that's not being attacked. 1 and 2 is actually the same if you think about it, if we just tweak it to consider one of the squares to block the king being the position of the piece. Then for 3, we need to know all the attack squares of the position. To do this, we can just initialize the attack squares when we create the board. But anyways, once we have the attack squares, we can just make the king move to the square that's not an attack square. But wait, aren't we forgetting about double checking? Well, this is actually really simple, because no matter what you do, the king can't block a double check. So all we need to consider is response 3, which is running. Last, we also need to consider pinning, since if a piece is pinned, it can't block a check. So we also need to factor that in. Speaking of pinning, let's move on to it. So you might think that this is quite complicated, since a pin is only a pin if there's only one piece between the king and the enemy piece. But there's actually quite a smart way of doing this. Firstly, we need to consider all the possible pinners, which may seem hard at first, because they are the pieces that are behind the pieces that are directly in front of the king. But actually, what we can do is just ignore the friendly pieces and use the same pretend the king is a queen strategy to get the closest enemy pieces in each direction. Now, once we get this, we can assume that the king is a queen again, which does not ignore its own pieces this time, and take its move squares. Then, we pretend that the enemy piece is a queen, and end it with the king's move squares as well as this directional mask. What? Yeah, look at this. If after the end, if the remaining bitboard is not 0, that means that there is a pinned piece. Even better is that it tells us directly where the piece is pinned. Nice. You can also see why this works, as for the king's movement mask and the bishop's movement mask, you can see that they don't have a similar blocker. So in the end, the bitboard is equal to 0, and we can find out that there's no pin. Okay, so now that we have that, we can need to do a similar thing for the check and find out the line and direction which the piece is being pinned, which actually has another clever strategy. To do this, we can assume that the pinned piece is a queen and get the move bitboard. Then we can AND this with the directional bitboard, as well as a directional bitboard from the king. And then finally, we just AND this with the square of the piece. Although this isn't really necessary, but I mean, it looks nice. Now that we have this, we can check whether the piece is pinned by ANDing it with the pinned bitboard mask. If it is pinned, we can get all its possible moves and just AND it with the pin mask along with the directional mask. Okay, just a quick cut in. We need this directional mask because in the pinning mask, we're actually could be storing more than one pin. So if we don't have this, the queen may say that it can move to some random location, which is not good. So that's why we need a directional mask. But this directional mask actually really isn't a directional mask. It's more of the direction from the king to the queen. So to get this, you use the directional mask of the king and you AND it with the directional mask of the queen, as shown here. Yeah. For knights, we just need to check whether it's pinned, and if it is, it can't move, so that's quite simple. And for pawns, we just need to check one edge case, which is if the pin is vertical. Otherwise, the pawn can't move either. Now, Sebastian Lake actually presented an edge case as seen here, where this pawn is actually pinned and can't en passant. But to fix this, I just did some really ugly hard coding, and I hope that'll work. And with this, we're finally done with finding all the moves. But wait, we might be able to find all the moves, but we're still not done with how to encode the moves. Just use a from square and a to square, right? Well, it's actually not this simple because of special moves like promotion. For example, how would the program know if you want it to be promoted to a knight? Or how can I encode en passant? How every programmer encodes their moves will be certainly different. Some might have an extra variable in their move structure, some might have a specific hash for each move, but how I did it was I just used the first 8 bits of my unsigned 16 int to encode the move. For example, the number 1084 might look random, but if you look at it in binary, you'll see the last 8 bits represents the number 60, which is the move to square, and the first 8 bits which have the number 5, which means that it wants to be a queen. How does it know it wants to be a queen? Well, I actually have an encoding scheme, which here it is if you're wondering. And you also might realize that I technically don't need the encoding scheme for castling and en passant, but hey, why not? You also might realize that now I need to add these special moves into my function which finds all the moves. So doing this for pawn promotion might be easy, just add it once it gets to the 8th rank, but en passant and castling actually needs additional information of whether the enemy has just pushed its pawn double or whether the king and the rook have moved. Since all of these are binary values, I decided that hey, if I'm gonna put bit manipulation to my resume, I might as well use it one final time. So I encode these binary values into another uint16 and pass it into the board once it's created. And finally, we're done with the board. So done, right? Remember how I said that this is my first C++ project? Well, yeah, let me share with you my day for the next 2 weeks. Step 1. Test my bot on position to see the number of child nodes given a certain depth. Step 2. Compare it with Stockfish. Step 3. What the f***? Why is it so off? Step 4. Spend 30 minutes trying to find the move that went wrong. Step 5. Spend an hour trying to find the error. Step 6. Rerun the program. Step 7. You gotta be f***ed. Step 8. Spend another 2 hours of bug fixing. Step 9. Get scolded by my teacher because I'm doing this during math class. Step 10. Spend an hour creating a Python script so I don't have to manually compare every move. Step 11. Repeat the process for another 2 weeks. But eventually, keyword eventually, I ran out of mistakes I can make and eventually did find most of the errors. I'm sure there are still a few, but that's for future me to deal with. Okay, after all of this, let's make it play its first game. Like we have discussed, we will be using the Minimax algorithm, and our evaluation function is simply just comparing which side has more pieces. But with that, I coded a Python interface because there's no way I'm finding out how to use STL. By the way, this Python script that communicates with the C++ exe is really ugly and took 2 weeks, but I'm just going to ignore that. With that, let's start. Okay, switching over to live commentary now. How to start everything up is number 1, you click the main file, and number 2, you click the main.cp file and give it a sec. Okay, I'm gonna play my first move, which is e4. You can see all the nodes here. And this is something I didn't talk about. I'll talk about in the next video. I'm just gonna take the knight here. Should be easy. Develop. I don't know what he's doing, playing all the same moves. Kinda cringe, not gonna lie. Ew! That's a terrible move. Okay, the bot took a bit longer to respond to that. Doesn't this... Oh, it doesn't fork. Huh. Maybe this instead. Trying to get there. Wait, but... if... What about... No, I can't play... Okay, let's try something... Okay, let's just go back. Let's chill first. Let's just not do anything too stupid. Okay, let's bring the bishop out. I'll be happy to trade. If Levy watches this, he'll probably cringe so much. Maybe push this pawn. Yeah. Okay, try to stack the rooks. Maybe. I haven't played chess in so long. Oh yes, rook stack, baby. Maybe. Okay, I guess I'll go here. Try to like come up. Oh, can this work? Maybe this. Does this work? Oh, here. Ooh. Oh. Shit. Wait, here. Oh. Yes! Wait, no, this is just mate. Okay, conclusion. The bot is shit, which is expected since it is still a work in progress, hence this is a two-part video. However, what is not shit is the number of nodes that it's able to search. Like, look at that speed. When compared to Stockfish, it is quite pathetic, but at the same time, I'm comparing it to the best chess engine in the world, so it is expected. Also, I am running this on my laptop, so here are the specs, and take that into consideration. But I'm still not satisfied with that performance, so let's face it against my Python chess bot. Earlier this year, I made a chess bot in Python. Also, it was dog shit, managing to search only 16,000 nodes in 10 seconds while, yeah, it's not even a competition. But it did have a lot of other algorithms that I did not discuss in this video, like a better evaluation function. So in a Sebastian Lake fashion, let's make them play 100 games against each other and see the results. Okay, so the final results are, drumroll please, 24 wins, 39 draws, and 37 losses, which seems pretty bad, but take into account that A, the bot has no idea how to checkmate, B, the bot is solely based off of material evaluation, and C, the bot runs much faster than the Python one. Okay, this video has become much longer than I thought it would be, so I'll just do some quick final thoughts. Can I cheat with this bot? I mean, not that I would want to, but no. Is this bot even remotely close to beating me? No. Does this bot have potential? Yes. So hopefully, I will make another video in the next month or so, showing some optimizations that I made to improve the bot, and hopefully it will be able to beat me. But until then, I hope that you enjoyed this video. Please like and subscribe because this took a long time to make. And thanks for watching. Bye.